No offense to anyone who likes pixel art games and thinks they look great, but I have to agree with you. Some of the most beautiful 2D games are made using pixel art. It's a celebration of the past. It's timeless, and it's usually cheaper and easier to produce. If you want to evoke nostalgia and spark imagination with crisply pixelated video games, you have to understand some of the fundamentals. Many pixel art games are made using tile maps, from platformers to tower defense or roguelike bullet hell shoot-em-ups. Tilemap is an image made out of multiple frames that can be seamlessly arranged into different patterns. Let's say we have this. We can use the same tilemap to create dirt surrounded by grass, or grass surrounded by dirt, or any other combination you need for your level layout. It's usually done like this. You have a tilemap image, you assign each frame a number, then we have a data structure, for example an array like this, where each number here represents one tile. In this class we will learn how to write our own levels as an array and convert them into game maps. We will create 3 different level layouts, and by the end of this class you will be able to make your own pixel art game worlds. This class is for beginners. A basic knowledge of programming principles is recommended to get the maximum value. I'm using vanilla JavaScript for everything as always, no frameworks and no libraries, so it's also very easy to convert this codebase into any other programming language if you want to do that. I add a button for debug mode to show and hide the game grid, just to make it more visual and easier to see how the game world is built tile by tile. We will be using just minimal CSS, so I might as well use a style tag up here. I give canvas some background color so that we can see where it is as we position and resize it. I do some global reset to unify the styles across different browsers. I spread the controls up top using CSS flexbox. I will center it horizontally using these 2 lines of CSS. I set canvas size with CSS to 320 times 320 pixels. I'm doing this on purpose. I will explain it in a minute. I give the buttons some padding. We linked script.js file down here, so to test it, I write a simple console log. It works. JavaScript is connected. Nice. Let's start by declaring some constants. I will spell them with all capitals like this. Game width will be 160 pixels and game height will also be 160. We are drawing pixel art. The tiles we are using are 32 times 32 pixels. You can find many tile maps with this size online. It's one of the most common sizes. We will start with just a small game world, 5 times 5 tiles. It will make it very easy for us to see how it actually works and how we can create a level as an array, and then we draw a game world based on that data. 5 times 32 is 160, so the canvas will be 160 times 160 pixels. HTML canvas has 2 sizes. Here we are setting the drawing surface size. We are drawing pixel art. I will scale everything we draw up to a double size. So the element size of canvas will be 160 times 2, 320 times 320 pixels. So this is the element size, the size of the HTML canvas element itself. It is a double of the drawing surface size that we declared here. When drawing on canvas, we need to make sure that the element size and drawing surface size are always the same, or they can be scaled up or down by the same factor to make sure the drawings are not distorted or stretched. We are scaling canvas up today, doubling the size of everything we draw. The game world will be a grid. Each tile in that grid is 32 times 32 pixels. We will only draw on canvas after everything on the web page has loaded, including all the resources like the tilemap image. Browsers are good at loading resources, so we are taking advantage of that here. Alternatively, I could build a simple custom assets loader with a few lines of JavaScript here. If you want me to show you how to do that, let me know. So after the page and all the elements are loaded, we set the canvas up. First, I create a custom variable and I point it towards the canvas element using its ID. Then I take that canvas reference and I call built-in getContext method on it, passing it 2D as an argument. This will create an instance of a built-in 2D rendering context that holds all canvas properties and drawing methods. I can console log it. If I open it here, we see the properties, canvas settings here. And down here we have all the built-in drawing methods. Today we are focusing on this one called drawImage. You can download the tilemap in the resources section below. It is copyright free. You can use it for your own projects if you want. You're welcome. I bring the image into the project here and I give it some ID. I hide the actual IMG element by giving it display none. Doing this will still load it into memory and we can access it using its ID. First, I will set canvas width to game width and canvas height to game height, like this. Then I bring the tilemap into the project using its ID I gave it, tilemap. All this code is inside load event listener to make sure it only runs when the IMG element is loaded and available. I can take ctx context from line 7 and I can call any built-in canvas drawing methods from it. drawImage method takes at least 3 arguments, the image we want to draw and x and y coordinates where to draw it on canvas. We have a pixel art image here that's 160 times 160 pixels. We are drawing it on a canvas element of the same size and then we are stretching the canvas to 320 times 320 pixels. We are scaling canvas element up. When we scale canvas up like this, the browser will try to smooth the image out automatically. But we are using pixel art. We want to preserve sharp pixel edges. Because there are some inconsistencies with cross-browser support, right now when I'm making this video, I have to do 2 declarations here. Crisp edges declaration will work in Firefox, but it will be ignored by Chrome. For Google Chrome browser, we have to set image rendering to pixelated. If you watch this in the future, you might not need both of these anymore. If I open the context object, Canvas has a property called image smoothing enabled, and it's set to true by default here. When working with canvas element, we have to remember that all these canvas properties will always reset back to default. These are the default values, and they reset back to them whenever canvas changes size. We are resizing canvas here, so we have to apply our custom canvas settings here after the resize. I set image smoothing enabled to false. I check, and it is false now. Now we have sharp pixels even when we scale them up. These coordinates represent the top left corner, and from there the image will be drawn. We can move it around by changing these values. This is horizontal X position, this is vertical Y position. We are drawing the whole image at its original size at these coordinates. We can also pass drawImage optional 4th and 5th arguments representing width and height. The image will be stretched or squeezed to fit the area we defined here. Now we are squeezing the whole tilemap image into an area of 1 tile. For clarity, I will put each argument on a separate line. So we are passing drawImage the image we want to draw and x, y, width and height where we want to draw it. If I jump by the increment of tile size, we can move around the grid. These values represent where the image will be placed on destination canvas, and these values represent the size of the image on canvas, the scaling. We can pass a drawImage method 4 more arguments to get the maximum control over the image we are drawing. I pass it source x, source y, source width and source height to define the area we want to crop out from the source image. Maybe I want to crop out a single tile from my tilemap, the one sitting on the top left corner. So we crop from coordinates 0, 0 to game tile, to set the width and height of the cropping area here. Okay, so we are passing it 9 arguments. The image we want to draw, source x, y, width and height of the crop, and destination x, y, width and height to define where we want to place that cropped out piece on destination canvas. If you play with these values, it should become obvious what they do. We have a tilemap image where individual tiles are 32 times 32 pixels, and we have a game world split into tiles that are the same size, also 32 times 32. Maybe I want to make this code base a bit more robust. Maybe you might have a tilemap image where tiles are 64 times 64 or some other size. We are using the same value for crop and for destination width and height, because the image I'm giving you matches my game grid. The tiles in the image are the same size as the tiles in the game world, but they don't always have to match, so I will create a separate variable representing a size of a single tile in my image tilemap. My tilemap is made out of individual frames of 32 times 32, but if I have a different one, I could change that value here. Image tile and game tile don't have to match. These 4 values represent the cropping area, so here we use the image tile value. These 4 values represent the placement on canvas, so here we need the game tile value. I can use increments of image tile here in source X and source Y arguments, and the combination of these will crop out a different frame in the tilemap. Again, if it's not clear, you can play with the values and it should become obvious how it works. To create a game world, we have to cycle over the entire game area in a grid, from left to right, row by row, from top to bottom. Whenever we work with a grid, we can use nested for loops, which means loop inside of another loop. I need to know how many rows and columns we have in our game grid. Rows will be game height divided by game tile. In this case, we have 5 rows. Columns will be game width divided by game tile. We have 5 columns. I check by console login rows and columns. Yes, 5, 5. To create a grid, we will use nested for loops, a loop inside of another loop. The outer for loop will travel over the game area row by row, from top, row 0, to bottom. Every time we enter a new row, we will cycle over the cells on that row from left to right, from column 0 to column 5. To visualize this, we start from row 0, column 0 here. We enter the inner loop, we cycle over columns from left to right. When we get to the end of the row, we exit the inner loop, the outer loop increases row by 1, we enter the next row, and again, the inner loop will map the cells on that row from left to right. We reach the end, the outer loop increases again, and we cycle over that row. We repeat this until we covered the entire game area. Every time we jump to a new cell in the game grid, we use built-in stroke rectangle method to draw that game tile. Width and height will be game tile, and the increments are also multiplied times game tile, vertically and horizontally. So as the columns increase from left to right, we are placing cells one next to another. And as the rows increment from top to bottom, we are placing rows of cells one under the other. This is a very useful code structure to understand when working with grids. Every time we jump to a new cell in the grid, we want to draw a frame from the tilemap. So I cut all this code and I paste it inside here. We know these 4 are the cropping area, and these 4 represent the placement of each tile on destination canvas. So I will simply place them the same way we are placing these rectangles. Column times game tile, row times game tile. We are positioning individual cells in the grid. Now let's have a look at the cropping position. For all cells in the grid, we are cropping out the same piece of the tilemap, because these are hard-coded values. The combination of these 2 coordinates defines which frame we are cropping out from the tilemap image. When working with tilemaps, we want to have some kind of a data structure that holds the layout of the game world. Up here, I create a constant variable I call level 1. It will be an array. We know that the game world is made out of 5 times 5 tiles. I made it small to make this part a bit easier to explain and understand. Once you understand how this works, you can create large, complex game maps. And later, we will also learn how to optimize them using off-screen canvas. As we create the game grid using the nested for loops on line 23, I want to be able to cycle over each element in level 1 array. Check what number we have here, and based on that number, I want to draw that tile from the tilemap image. I chose tile 9 here as an example. I break lines here like this to make it visually clear. You can see that this level 1 data array exactly matches the size of my game world grid. I need a way to cycle over the game grid one tile after another, and for each tile to check that particular index in level 1 array to see what number is stored there. That number will represent tile in the tilemap image, and we want to crop out and draw that particular tile for that position in the game grid. I create a custom function I call getTile. It will take a game map. For now we have only level 1. We pass it column and row. We are currently cycling over, and we want this function to give us an index and a value that sits at this index inside level 1 array. Inside the data structure, the array where we hold the configuration of the level. Because we structured level 1 array the same as the game grid, the indexes in this array go in the same order as the cells in the game grid. GetTile will give me a number value we hold at that index of the level 1 array. This is a bit challenging to understand, especially if this is the first time you are dealing with grids, but don't worry, it will make more sense if you use this more often. The formula to get a single index value based on a row and a column is this. All the completed rows times columns plus the current column. To visualize this, let's say we cycled over the game world tile by tile, and we are on this tile right now. We want to know which index in level 1 array corresponds to this position in the grid. We have completed rows 1 and 2, and we are in the column 1, 2, 3 after that. The formula we have here will give us the total sum of cells in the whole completed rows. In this case, we completed 2 rows. 2 times columns is 2 times 5. We have 10 cells. Plus how far we are into the new row, 1, 2, 3. We are on position 13. It will return 13 for this cell. Let's say we are here, 0 completed rows, plus 1, 2, 3, 4 columns. It will return 4. Or here, 3 completed rows, 3 times 5 is 15, plus 1, 2, we get 17. So complete rows plus however many cells we are into the new row. Map will be this level 1 array. Column and row will come from here, from the nested for loops as we cycle over the game grid. Each time we enter a new cell in the game grid, I want to get that index value in the game map and the value we store at that index, which represents the tile we want to crop out for that position in the game grid. I pass it level 1 from line 7 as the game map. I pass it column from here. And I pass it row from here. GetTile method will give us that single number representing a tile we hold at that index in level 1 array. Currently, we set all of them to number 9, which is this tile. So now we are cycling over the game grid. We are checking level 1 array to see which number we hold there for each cell. We set them all to number 9. I need to convert that number 9 into cropping x and y coordinates in the tile map. We know that the values we pass here to drawImage method represent the cropping x and y position of the frame we want. My goal is to write some code that will know that when tile is 9, we need to crop out this part of the tile map. Or when the tile on line 33 is 2, we need to crop out this bit. We need to extract x and y coordinates from that single value of 9. The horizontal cropping position is basically how far from the left side of the image we want to start cropping. I will simply take the tile number times the width of a single tile, and I use modulus operator, whatever is left over from the width of the image. We will use remainder operator. The remainder operator returns the remainder left over when one operand is divided by another operand. We know the tiles are 32 times 32 pixels. If tile number is, for example, 7, 7 times 32 is 224 pixels. 224 modulus 160 is remainder of 64. We will get a crop in position 64 pixels from the left edge. As we said, the remainder operator returns the remainder left over when one operand is divided by another operand. Inside the level 1 array, we set all tiles to be number 9 for now. 9 times 32 is 288. 288 modulus 160 is 128. That will give us the horizontal start of the cropping area here. This is almost correct. We will get back to this in a minute. We also need the vertical cropping position, which is much more simple to calculate. Look at the tile map here. We know that all the tiles on this row will have to start from cropping coordinate 0. All these will have vertical y coordinate of 32, 64, 96, and so on. So the cropping vertical coordinate is shared for all tiles on the same row. To get that value, I need to know how many frames we have per row in the tile map. Constant variable image columns will be the width of the tile map image divided by a width of a single tile. In this case, it will be 160 divided by 32, which is 5. Kind of accidentally, my tile map matches the game world. It's 5 times 5 rows and columns, but it doesn't have to be like that. And this code will work whatever the size and the layout of the tile map is. To get the vertical cropping coordinate for each row, I want to divide the current tile by the number of tiles per row. And I want to multiply that times the size of image tile. We need integers, no decimal point, so I use math.floor to round it down to the nearest integer. Let's say the tile is 9, this one. 9 divided by 5 is 1.8, and math.floor will give us 1. 1 times 32 is 32. The vertical cropping coordinate for tile number 9 will start from here. So now, if I change the tile numbers in the map layout here, I'm almost getting the right tile. I'm getting one tile to the right than the numbers we see on the schema we created. When I put 1 here, we get this one. When I put 2, it gives me this one. 3 gives me this one. I need to do -1 here because we are cropping from the top left corner. This will move the cropping position 1 image tile to the left. For the vertical position, look what happens when I do tile 5. I actually get this frame because it's breaking to another line 1 tile early. Again, we need to do tile -1 to break to the next line at the right point. When I do tile -1, that edge tile will now show me the correct frame 5. Basically because of the fact that image coordinates and cropping areas are defined by x and y position of the top left corner, we need to do tile -1 here to correctly map these values. Right, so this was the most challenging part. Once you understand this, tile maps are very easy. Don't worry about it too much, repetition makes it easier to understand. Now I can just have a look at my schema that I created here, and in this representation of my game level, I can assign each cell a different number, and the correct tile will be cropped out and drawn. The image I'm giving you is quite flexible. Now I'm using it to create a simple forest scene where a patch of dirt is surrounded by trees and grass. Normally the world map would be much bigger. I chose to do a simple 5x5 game world because it's easier to visualize the rows, columns, breakpoints, and so on. All the things we just learned about. I was trying to show you on a very simple example. I have this debug button here. When we click it, I want to show and hide this helper grid that separates individual tiles. Let variable I call debug. Initially I set it to false. I only want to highlight the cells with stroke rectangle if debug is true. Debug is false, debug is true. I can connect this to the button we created here. We are still inside the load event listener. Constant variable I called debug button, and I point it to the button element using its ID. Here we will define controls. I give it an event listener for click event. When we click, it will set debug from line 32 to its opposite value. If it's true, we set it to false. If it's false, we set it to true. Debug equals the opposite of debug. I console log it. When I click the button, you can see I'm getting true, false, true, false. We are toggling debug mode on and off. The grid is not disappearing, and that's because we are only drawing everything once on the first page load. I actually need to redraw the game scene when something changes. To redraw the game grid with all its tiles, I need to run this code again. So let's put it into a function I call drawLevel. I put all of this inside. So here we define the function. Here I call it on the first page load. And here I call it whenever debug button is pressed. Now, every time we press the debug button, we redraw the level, and depending on the value of debug variable, we either draw or don't draw the game grid, as we defined on line 49. Now that we know how this works, we can create another level, level 2. And I change some of the tiles, 24, 24, 25, 24, 25. That will be the top row. I can draw it by passing level 2 as the game map here. But maybe I want this to be dynamic, so let's change this into a variable I call a level. It will be expected as an argument. We define it up here, and initially we set it to level 1, which holds the tile layout for a patch of dirt surrounded by grass. drawLevel expects that level as an argument, so I need to pass it there in all places where we call drawLevel function. Here, and also when I press the debug button here. Let's draw level 2. I set the default to level 2, so we see it as I build it. And debug will be set to false by default. I can still toggle it on and off by clicking the debug button. Level 2 will be kinda the opposite of level 1, because I want to show you how to use the same tilemap image to create a patch of grass surrounded by dirt. The tiles will still connect. 21, 2, 2, 2, 22. And the bottom row will be 19, 20, 19, 19, and 19. We have a patch of grass in a forest. So this is level 1, this is level 2. Very different layouts created using the same tile map. I will build level 3 now, but I encourage you to use different values here to make level 3 your own unique layout. I set level 3 as the default here. I created these 3 buttons here. I want to be able to switch levels by clicking them. Same as we did here with the debug button, first I create a reference to all 3 level buttons using their IDs. Then we attach event listener for click event to level 1 button. We set level variable from line 49 to level 1. And after that we redraw the level, passing it that new updated level map as an argument. Level 2 here, like this. And level 3 here, like this. I can now click level 1, level 2, and level 3, and we draw different game world layouts. Now it's time for you to design your own compositions and tile combinations. We covered the fundamental principles of tile maps. We can do so much more here. Maybe you want your tile map to have multiple layers, so the objects can overlap and our player character can actually walk around the trees. If you want to build large scrolling tile maps, there are many optimizations we can deploy. Because canvas logic and rendering happens on the same thread as user interaction, maybe we want some demanding computations, such as building a large game world, to be offloaded to a so-called worker, which is a separate thread that runs in the background. And we leave the main thread free to perform more user-critical tasks. This will greatly improve the speed and responsiveness of the game, and it is also quite easy to implement. Check out this class if you want to learn more.